Okay, that concludes all company business. We'll get on with the show. Instructor Abby West holds a PhD in paleontology from Columbia University and a BA in organismal biology from the University of Cambridge, UK. Dr. West moved to Pittsburgh to complete a postdoctoral fellowship at Carnegie Museum of Natural History in the Section of Paleontology and the Section of Mammals, and now works in the Department of Biological Sciences at Pitt. She's the first Pitt instructor we've had for any class over 17 years, so welcome, even though you're playing for the enemy. Teaching classes on molecular genetics, evolution, and science communication. Dr. West has carried out paleontology fieldwork in several different states, the UK and Antarctica. Dr. West.
All right, thanks for that introduction. My name's Abby. I'm a paleontologist. I know you've been talking to paleontologists for the last 6 weeks. I'm a slightly different kind of paleontologist. I don't study dinosaurs. I study mammals, which is what everybody in this room is, right? We're warm-blooded, we have fur or hair, we nurse our young, we give birth to live young instead of laying eggs. Mammals are easier to sympathize with in some ways, right? They're like, we can look at a dog and a cat and like, you know, an elephant and think, yes, that's like me in some ways. And we also have this story about mammals that we learn when we start to learn about dinosaurs, which is that dinosaurs really ruled the Mesozoic, right? There was this era of dinosaurs. They were stomping around, eating all the food, all of the other animals and all of the plants. And they didn't really give mammals any room to thrive or survive until the dinosaurs went extinct. That's the story, right? That's what we sort of believe. And I'm here to tell you a little bit about some of the mammals that were alive at the same time as the dinosaurs and what they were doing, or as far as we know what they were doing, what they looked like. And then we're going to talk a little bit about how that group of mammals gave way later on, at the same time that the dinosaurs were going extinct, to make room for the group of mammals that we see walking the earth today. So all of the amazing diversity of different warm-blooded, furry animals that we see on the earth today, right, from bats to tigers to polar bears to horses to humans, originated really after the dinosaurs were gone. And this sort of, all the different habitats that these mammals now occupy were available during the age of dinosaurs, and some of them actually were occupied by mammals as well. And we're just sort of starting to learn about this. We're just sort of starting to learn about what mammals were doing while the dinosaurs were kind of being very charismatic and large and ruling the earth. Because we're starting to study and find new fossils that are telling us these things, and fossils that look an awful lot like some of the mammals that we know today. So I guess my point is that the classic story of mammals being these little scurrying underfoot things until the dinosaurs went away is only part of the picture, and the real picture of what was going on in the Mesozoic is a lot more exciting. Let's sort of start out by thinking about modern mammals. And I mentioned a little bit, you know, some of the diversity that we see, but actually some of the major extremes are totally unprecedented, what we see on Earth today, right? So we have the largest vertebrate, in fact, the largest animal ever to live on Earth is a mammal, right? This is a blue whale. And we have some of the smallest vertebrates ever to live on Earth alive today as well. We have a shrew over on the left, and we have a bumblebee bat, which is called that because it's about the same size as a bumblebee. Mammals that are alive today are also some of the fastest animals on land. Do you know what this one is?
Cheetah.
Yeah. And some of the loudest. What are these animals?
Howler monkey.
That one's a howler monkey. And this one?
Whale.
Yeah, the sperm whale makes the loudest call of any animal on Earth. Those are mammals. They live in some of the most extreme habitats, especially, for instance, some of the coldest habitats. because they're warm-blooded and furry, and they can manage to keep their metabolisms going in very cold environments. They also have big brains and unique sensory adaptations that go along with having those big brains. Lots of different mammals can echolocate, so they can use sonar to find their prey and to find their way around their habitats. And we don't know of any other animals on Earth that can do this or ever could do this. My examples here are a bat. You know, bats make those little chirping sounds. You might have heard them when they swoop overhead, right? They're using those chirping sounds as sonar to tell where the trees are so they don't run into them, and to tell where the bugs are so they can catch them. Dolphins can do this too. Lots of different dolphins and whales can do the same thing. Mammals also have an amazing sense of smell. This over here on this side is a star-nosed mole, and it has these tentacles coming off of its nose that enable it to pick up really, really tiny little, very low concentrations of chemicals in the soil, in the water, and in the air around it. That's a sense of smell. And they have whiskers, adaptations of that very fur that keeps us warm and defines us as mammals, that are sort of an extension of our sense of touch. So cats and dogs have whiskers, seals like this one in the picture have whiskers. That's a sensory adaptation that lets us interact with our world as well. And that's unique to mammals too. So all of these things, all of these different amazing ways of interacting with the world, are things that are not found in any other group of animals, even dinosaurs, even birds. And you might ask, while you're thinking about all this diversity, how long would it take for all of this to evolve? Because we know that there's like one ancient mammal ancestor, right? That like gave rise to all this diversity over some period of time. How long would it take to go from that small little first fluffy mom of all of the mammals to all of this amazing diversity that we see, from polar bears to howler monkeys to cheetahs to tiny little bumblebee bats to blue whales? You might have some sense from the previous talks about how long it took to go from the first dinosaurs to the big T-Rexes and to the Archaeopteryxes and sauropods and things that we saw later on in the Cretaceous. How long of a period of time, does anyone remember, that was, like in millions of years? At least 7. Yeah, it was a couple hundred. It was a couple 100 million years, right? Which is a long time, right? If you can imagine 100 years and then multiply that by 1,000,000, that's a long time. That's a lot of generations of dinosaurs, right? Mammals, all of the mammals that we've just looked at, evolved all of this amazing diversity in 65 million years, since the extinction of the dinosaurs, which is really rapid when you think about it. So we'll look at that in a second, but one thing I do want to mention is that those 200 million years or so while the dinosaurs were around, there was mammal evolution going on as well. Mammals first appeared around the same time as dinosaurs first appeared. So the question of how long all of this diversity has been evolving can be answered with 65 million years. But the question of when did mammals first appear, that's a much longer time period, right? So what were they doing for the first 200 million years before they exploded into all this amazing diversity that we know of today? Let's look. So if there's any like taxonomy nerds, in addition to me in here, you might be used to looking at taxonomy in the form of branching diagrams. Did Lindsay or Tyler, is it Tyler, show you any branching tree diagrams in the last couple of weeks? Yeah. So these are kind of just summaries of the family tree, basically, that we're looking at. And I know it's probably kind of small for you to look at up here. I didn't know how big the screen was going to be. But what you can see is that this branching pattern starts in the bottom, in the green bar along the bottom of the screen, which tells us that both of these groups of animals started branching off, started creating different groups and diverging into having different traits and different appearances at about the same time, right? And we're down in the Mesozoic here. So you might imagine Mesozoic mammals as this kind of typical story, little mouse-shaped insect-eating guys running around, scuttling around underneath the feet of dinosaurs, right? And you know that modern mammals have all of this wonderful diversity. We have animals that hop, we have animals that swim, we have animals that fly, which is an incredible adaptation. But we don't really know what happened in between. Right? So if we want to look back in the fossil record and look at the fossils that we find around the dinosaur fossils and say, well, which one of these were mammals? There's some traits we can look for in the fossils that will give us a clue. If we want to know what mammals were doing while the dinosaurs were still alive, we can find those fossils, and we just need to be able to identify them as mammal fossils, right? So there are some traits we can look for. And these are all traits that modern mammals have as well. So we can infer that if we find those in fossils, those must be mammals too, right? And some of these traits are familiar to you, perhaps. Some of them we've mentioned already. For example, having fur, nursing their young. Some of them are not familiar, probably, to you. For example, having an ear that's separated from the jaw. What does that mean? We'll look at that in a minute. Having a secondary hard palate. You might be able to imagine what that means, right? What's your hard palate? The roof of your mouth, right? Yeah. That's a mammal trait. Dinosaurs don't have that. Meaning that their nose and their mouth open into the same cavity. They can't, for example, do this. Can't breathe while they're eating, in other words. If I was a dinosaur and I tried to do that, soda would have come out my nose. Because they don't have a hard palate to divide the nose and the mouth, right? Mammals also display determinate growth, which means that when you reach adult size, you stop growing. Dinosaurs didn't do that, right? They just grew bigger and bigger throughout their whole life. And mammals only replace their teeth once. Have you guys lost any of your teeth? Do you expect that you might lose the next set as well and replace them again? Probably not, right? Just one go at all of that. Dinosaurs, anytime they lose a teeth, they can replace it. Mammals, you only get one shot. Some of these things we can see directly in fossils, right? We can see determinate growth in fossils, and we'll look at a second about how you can do that. We can see a secondary hard palate in fossils. It's made of bone, right? It fossilizes. We can't necessarily see nursing young with milk, but we can see some kind of features that are correlated to that kind of behavior. And we'll talk about that in a second too. The first trait is the first one on that list, which was ear separate from jaw. What the heck do I mean by that? I mean the bones of the ear are not touching the bones of the jaw. Does anyone know what I mean by the bones of the ear? What bones do you have in your ear?
I can't name, but they're in there.
They're in there, right? They're really small. They're the tiniest bone in the body is in your ear, right? Does everyone know the ones I'm talking about? They're attached on one side to your eardrum and on the other side to your skull. And they amplify the airwaves that move your eardrum so that the nerves in your brain can pick them up. That's unique to mammals, having all of those three little bones in the ear. In lizards and in dinosaurs and in all other animals with backbones, all other vertebrates, the jaw joint is touching the ear bones. Whereas in mammals, the ear bones are floating in that special little space inside your middle ear, and they can move independently of the jaw. Do you imagine that makes us better at hearing or worse at hearing than lizards? What would a lizard hear if its ear bones are attached to its jawbone?
Eating,
Yeah, it might.
anytime there's movement in his jaw.
Yeah, so its jaw movements are going to interfere with its hearing. Also, those bones can't really move freely in the air, right? So, do you think they can hear very quiet sounds, very loud sounds? Mammals are better at hearing than lizards, right? We can hear very quiet little sounds. We can hear very high-pitched sounds, which, if you'll forgive me for flipping back and forth between slides, might explain why so many mammals are so good at using sonar. Right? We have this amazing ear that lets us pick up on very little tiny sounds that other animals can't sense. And because we're talking about bones here, we're also talking about things we can see in the fossil record. And we can actually see in the fossil record of mammal-like reptiles and their mammal relatives, we can almost see the exact moment where that separation took place. So on the left here is a mammaliform, which means it's a mammal-like animal, but it's not quite a mammal, right? It's a close relative, but it's not totally a mammal. And one of the things that makes it not totally a mammal is that those ear bones that are colored in orange here are attached really firmly to the back of the jawbone. So that jawbone is like a lower jaw. It's like one of these. Whereas on the right, this is a fossil mammal that has an ear bone that's totally separate from its jaw. And actually the picture in orange here, can you all see? I'm not quite sure where I am in between you and the screen. The picture in orange here for the mammal one is blown up to a much larger scale because those bones are already much smaller by this time. And they're not touching the back of the jaw, and we can tell that even if we don't find a fossil of these little tiny bones, we can tell that they weren't attached because there's no place for them to attach in the back of the jaw. So that's our clue. When we find a fossil jaw that has no place for those ear bones to attach, we know we found the fossil of a mammal. It's easy to imagine when we're talking about transitions like this that it took place once. Everything before that transition was a mammal-like reptile, and everything after that transition was a mammal. But this is an adaptation that has many advantages, right? To be able to hear those tiny little sounds, to be able to have a more mobile jaw. And it turns out that actually that transition probably took place several times. One of those times was on the lineage leading to modern mammals, but a few other times took place in the mammal-like reptiles as well, which shows us that it really was very advantageous. If we see a trait appear more than once in multiple different unrelated groups, we can imagine that it was probably very useful at the time. And even though only one of those lineages actually survived, it was probably useful for all of them. So that's one of the mammal traits that we can see in the fossil record. But obviously, alone, it's not enough to tell us that we're looking at a fossil mammal. Another trait of mammals, which is one that's pretty obvious to us all, is that we have fur. And sometimes we can see fur in fossils. Can you see the fur in these fossils? Let's just take a look at them for a moment. Where's the fur here? So we can see we have like skeletons, right? These are bones and skeletons. There's a rib cage. There's a skull. Over on this side, we have one that's kind of doing this position. Right? You can see his arms and his rib cage. His head up here. Where's the fossil fur? Yeah,
places around the fossil.
Exactly. So all of this, and all of this, and then over here on this guy, all of this stuff, that's like some carbon film that's a remnant of fur. These are very ancient fossils, right? These are dinosaur-aged fossils. And they still have preserved in them this remnant of fur. So these must have been very furry animals, actually. And here I have some artists' imaginings of what these animals would have looked like. So same on the left here is the one on the left here, and the one on the right there is the one on the right. They're cute, right? What do you think was good for them about being covered in fur? If you're a small little mammal living in the age of dinosaurs, you can see how small the one over here is because it's eating a bug. It's holding a bug like this in its hand. What are some advantages of being furry?
Heat.
Heat. Yeah, it keeps you warm. Can you think of any other advantages of being furry?
Could it be camouflage?
Could be camouflage, yeah. In fact, we don't see a lot of very brightly colored mammals, do we? I mean, I guess we see like tigers and zebras, and they're fairly loud patterns, but those patterns actually contribute to their camouflage as well. A lot of mammals are very cryptically colored or camouflaged. And then some of that fur is probably adapted into whiskers, so they can sense their environment by touch as well. And that's useful because a lot of early mammals, especially those from the age of dinosaurs, were nocturnal. They were active at night. So they weren't using their eyes to sense their environment probably as much as they were using their sense of touch and their sense of smell. So that's the second feature that we can look for in the fossil record. We can also look for a secondary hard palate. So let's just talk about some of these pictures. This is a kind of diagram that maybe takes some getting used to looking at, but we're looking here at a cross-section through the snout of an animal, right? So you're looking like, if it was like a snout coming out like this from the face of a mammal, we're looking at a cross-section through here. And you can see that the secondary hard palate makes this tunnel where air that goes in and out of the nose can go to the trachea, bypassing the mouth completely, meaning you can breathe and eat at the same time. Nobody else except mammals can do this. Birds have to swallow their food quickly so then they can take a breath and then take another bite. Why is it useful for a mammal to be able to breathe and eat, or breathe and drink at the same time? Thinking about all the things that we know mammals do. What do you think?
So they can run.
Ah, yes, that's actually a really great point, so they can run. Mammals do a lot more aerobic activity than other animals of their same size, right? If you imagine a lizard, lizards spend most of their time sitting as still as possible and then running a little bit when they're in danger or to catch food, right? Mammals are running around all the time. So they need to be able to get enough air into their systems. Definitely. What else? What else can be enabled by being able to drink and breathe at the same time? Especially maybe like if you were a baby mammal. Were you going to say that too? Yeah, so they can nurse. So if you've ever seen a baby nursing, right? They don't hold their breath while they're attached. They're breathing and drinking at the same time. And that's really important. That's critical, because it means that mammal parents, or mammal moms in particular, can feed their young continuously, right? They can get all of the energy they need to build those big brains and all of that fur and all of the muscles that they need to be active animals. So on my list before, I had nurses young with milk, and that's not something we can see in the fossil record, but something like this shows us that an animal would have been able to do that behavior. So let's go back to that list. So we've seen the ear separated from jaw. We've talked about how that helps mammals sense their environment in a unique way. We talked about fur and how that helped them be active, for example, if it was cold, helped them camouflage. We've talked about the secondary hard palate and how it shows us that they were probably able to nurse their young with milk. If we find a fossil that has a secondary hard palate. And now we're going to talk about the remaining two. Do you have a question?
Another thought on ear separated from jaw. You can hear while you're eating, so you're not eating and being eaten.
Totally. Yeah, and that's really useful, right? Especially if you're a small little mammal that's living around big predators. It's useful when you're crunching on a bug to be able to hear predators coming. Totally. So the last two features that I wanted to look at are determinate growth, meaning growing to a certain size and then stopping, rather than growing for your whole life, and only replacing your teeth once. And my point is that if we see all of these in an individual, we know that that was definitely a mammal, right? So how can we see determinate growth in the fossil record? By which I mean, how can we know that a fossil had reached its maximum adult size? Sometimes in fossils, the internal structure of the bone, as well as the external shape of the bone, is preserved. You know that fossils are bones that have been replaced by rock, basically, right? They're mineralized. Sometimes that mineralization actually captures the internal features of the bone itself. And that's useful for us, for example, when we're looking at the bird-dinosaur transition, when we're looking at trying to decide which dinosaurs, which early birds were able to fly. You know, birds have hollow bones, right? So sometimes fossils will capture that, and we can see hollow bones in animals like Archaeopteryx. In this case, we can see the microstructure of a bone has some features that only appear when the animal has stopped growing. In particular, we see this external fundamental system, which is a region of condensed bone that's around the outside. And you can kind of think of it as like the bark on a tree, right? It's just a region of the bone that has a different structure. And in this picture, we're looking at a cross-section. If you want to think of it as like tree rings, we've zoomed in, right? So the circle of the bone would be big. We've just zoomed in, and we're looking at a cross-section through the bone. And this is the outside surface. And this, I don't know if you can see the texture from where you are, but this is a much denser ring on the outside than anywhere in the middle. And that only forms in an adult animal that's stopped growing and has started putting its energy into strengthening the bones it has rather than making them larger. So we can find out if a fossil animal had determinate growth by chopping it up and looking at it under a microscope. We can also find out if a fossil animal had determinate growth by doing like a high-resolution X-ray of the bones and looking at the structure that way. Right? Do you think it's useful to be able to reach adult size and stop growing and be able to put energy somewhere else than growth? Why do you think some animals do that and other animals keep growing their whole life? This is a difficult question. It might be worth maybe just like turn to the person next to you for a second and just like think about that question with them. Because it's true that we do see continual growth and determinate growth in animals that are alive today. So they're both adaptations in some ways. Let's talk briefly about why it might be good to stop growing. Yeah.
To stop growing, if you keep continuously growing, you're going
saved by stopping growth. For example, maybe then you're able to use more energy feeding your young, reproducing, right, instead of growing yourself. Anyone think of any other reasons why it might be good to stop growing at a certain point?
Keep growing, you become unwieldy. Just unwieldy.
Yeah, so maybe there's some like mechanical reasons to stop growing, right? Maybe it's like you're able to be stronger and faster if you remain a certain small size. Those are both really good explanations. So having energy to put into reproduction and having or retaining some agility, both of those are really good reasons that mammals undergo determinate growth. They stop growing. Another reason is that if you want to have really specialized interlocking teeth, your jaws need to be the right size for them to fit. If you keep growing, imagine if you had the teeth you have now, because mammals only replace their teeth once, but your face kept growing. Would your teeth occlude correctly after a while? Or would they be kind of all over the place with gaps in between them? All over the place, right? And mammals really rely on having that complex set of biting surfaces on their molars to chew up their food. And if we were growing continually and replacing our teeth continually, we wouldn't have that perfect mortar and pestle situation with our molars. Dinosaurs don't have molars, right? They just have like a mouthful of knives. Mammals are unique. We have this really highly adapted, perfect chewing mechanism. Why is it useful to be able to chew our food? I mean, dinosaurs did pretty well just biting off hunks and gulping them down whole, right? Why do we prefer to chew before we swallow?
For nutrition.
For nutrition, yeah. So we've talked already about how, we're devoting a lot of energy to feeding our young. We're devoting a lot of energy to our big brains and complicated sensory adaptations. We're devoting a lot of energy to keeping warm and being active in these extreme environments. We need to get that energy from somewhere, right? And so chewing our food is one way to do that. So I have two examples here of animals that lived around the same time, probably in similar habitats. One of them has the ability to chew, and one of them just has the ability to bite and gulp. So Morganucodon here is a mammal, and it can chew its food. It has those molars that are able to grind food up, as well as teeth up front that are able to grab and pierce and cut food. Whereas Thrinaxodon over there on the left just has sharp cutting and stabbing teeth. So this would have been just gulping down food whole. And if this works, I'm going to show you one of the ways that paleontologists study fossils like this when we don't have the fossils themselves in front of us. Because these are like, although there's fossils of mammals all over the place, they're like in museums and hard to come by, and sometimes they're very small and hard to see or fragile to study, right? So one of the things we can do that I think is really cool is make these virtual 3D models. Is this coming up here? How do I get this to come up here? Here we go. We can make these virtual 3D models. And then we can study them and look at them, and everyone can study them and look at them. And I can send you all the links to these if you want to have a look at them later on your devices. I think you can probably pull it up even on a phone. But you can learn a lot more about the morphology of things by looking at them in 3D than you can by looking at a picture. Right? So this is our first example here. What kind of teeth are you seeing in this animal? Are we seeing knife-like teeth, or are we seeing grinding teeth? Sharp? Yeah? Stab? Yeah, definitely. This is stabber face. This is Thrinaxodon. You can also see he has a tiny little spot for a brain if you look. These are where his biting muscles would have been. This is where his brain would have been. Not a lot of thinking going on, just grabbing and stabbing.
Shred more than chew.
Shred, yeah. Definitely a shredder. So that's our mammal-like reptile. Let's find the other one here. Now we're going to look at a similar model of a mammal. An early mammal, but still a mammal. Okay, I'm going to move the model around and you can talk to me about some of the differences you're seeing. Any differences from this angle?
Skull is longer.
Longer skull, yeah? Anything about like the, yeah, what's that?
I don't know what it is.
So this is like his cheekbones, right? Going out there.
Yeah.
And if we look at the other guy, I wonder if I can bring them up side by side actually. Whoops, almost. There we go. If we look at the other guy, he has those big cheekbones too, right? They're a lot more robust though. They're bigger, fatter bones. So he has bigger chomping muscles than our mammal friend has. How about where the brain was for each of these guys? Any differences? I know you can't quite see them, but there we go. Any differences you can see?
Shielded.
Bigger area.
Bigger area for the mammal?
Yeah.
Yeah. What else?
Shielded.
Which one? This one? Yeah. So there's a lot of bone around that brain, as well as being a bigger space for the brain to reside in. In fact, it looks like it's just donating more real estate of the skull in general to brain than to stabbing, biting muscles.
Or the skull than the cage.
Yeah, totally. More actually sort of skull-like looking morphology here. Let's look at the teeth. What do you notice about the teeth? Maybe the sizes or the shapes of them. What can you see that's different? There's lots of possible things you can see.
Some of them are like clumped together.
Some of them are clumped together. Yeah, totally. So like these ones over here, there's like more space between the front ones than the back ones maybe, right? That's what I'm seeing at least. Totally. So there's more differentiation, in other words, between what's happening in the front of the mouth than in the back of the mouth. We use the front of our mouth for slicing, like our incisors, our sharp teeth up front, and we use our back teeth for grinding, chewing. Right? And this is a very early mammal, but we're already able to see that here. Yeah.
The nasal passages are different too. The one that's
Yeah.
looks a lot more narrow.
Which one looks narrow?
That one.
This one? Yeah, there's difference in the snout shape, definitely. And in fact, I'm not sure if we can see it here. Oops, don't zoom in, turn. I don't know if we can see, yeah. Can you guys see the hard palate in each of these?
Yes.
Okay, let's point it out. So now we're looking up at the underneath of the skull. Might be a little bit difficult to see. There's an opening here. That's where the nasal passageway from the nostrils at the front of the snout opens back and joins the trachea, the back of the throat of this animal. Over here, there's a great big opening, and it's in the middle of the roof of the mouth. Which means that probably in this mammal-like reptile, the secondary palate was not complete. Meaning, what was this animal on the left here probably not doing with its young? It didn't have a complete division between nose and mouth. Probably not nursing them, right? So this animal probably didn't have the ability to very effectively eat while breathing. So that's all of the traits that we were talking about, that we can see related morphologies in the skulls themselves. How do I get back to the PowerPoint? Let's see. Okay. So complex teeth is really important because it means we can chew more efficiently, right? We can get all of the nutrition out of whatever we're eating. And it means that we can be super active And we can be super intelligent and have really sharp senses and be very agile. And that's really important for mammals, especially ones that are living around big dinosaur predators, especially ones that are preying on dinosaurs, which some of them did. Especially Mesozoic mammals that are flying and swimming, which some of them, it turns out, did. So although they were probably, still relatively small, the largest Mesozoic mammal were probably sort of cat size, they were still doing all of these different activities that all of those special mammal traits enabled them to do. And they were doing things that dinosaurs couldn't do, like living in water and gliding through the air. They were really highly adapted to all these different habitats. And they were really good at using those resources, at nursing their young, at sensing their environments, at avoiding being eaten by dinosaurs. And we're really only just discovering that. And that's why we have this story in our minds that the dinosaurs overshadowed mammals, and the only thing that let mammals get as diverse and interesting as they are was the death of the dinosaurs. That's not necessarily the full story, right? But it does turn out that a lot of this Mesozoic mammal diversity was wiped out by the same extinction that killed the dinosaurs. Which means that actually, a lot of the diversity that we see today really did only appear in the last 65 million years. And actually, the mammals that we see today are even more unusual and extreme than the ones we know about from the Mesozoic, right? This was the biggest Mesozoic mammal. We can do better today, right, with our blue whale. We have completely aquatic mammals today. We have powered flying mammals today, not just gliders, right? We have bats. So there were a lot of things that perhaps the dinosaurs were overshadowing or preventing from taking place. And what happened after that extinction, in particular, one of the big things that happened was that mammals got very large. We started to see elephants and whales and horses and all of these really big animals that we just didn't see in the Mesozoic of mammals because we had dinosaurs occupying all of those niches already. There's two ways, this is just an explanation for why those niches were occupied, right? There's two ways to be a large mammal. One is you are a very big plant eater, and the other is you are a very big predator. In the Mesozoic, who was eating most of the plants? In the age of dinosaurs. The big dinosaurs, right? Dippy and his relatives. And they were eating all of these amazing diversity of flowering plants. And that's one thing that let them become so large, right? Flowering plants first evolved during the age of dinosaurs. Oops. Oh no, I went too far. Sorry. Go back. So although there was a lot of plant around to be eaten, mammals didn't really get a look in because dinosaurs were already occupying those big plant-eating niches. The other strategy is to eat other large animals, and dinosaurs and their relatives were already occupying those niches as well. We have dinosaurs like T-Rex, we have crocodile relatives like these big, terrifying, predatory, galloping crocodiles that were around at the same time as dinosaurs. We have marine reptiles like the mosasaurs that you saw in the latest Jurassic Park movies, and we have gigantic pterosaurs. And all of these things were doing great and preventing mammals from getting very large until the extinction, the KPG extinction. And the only things that survived on land of those two amazing groups of mammals and birds were some of the more advanced mammals and birds, right? So the avian dinosaurs. And some of the things they have in common are having a high metabolism, being very active, and being really adaptable to different habitats, being able to live where it's very cold and very hot, being able to regulate their own body temperatures, essentially, right? And so all of that dinosaur diversity was wiped out, and all of that Mesozoic mammal diversity was wiped out, and really we're left back at square one. Basically where we started at the beginning of the age of dinosaurs. And so it's true, the answer to the earlier question was, it is true that all of the mammal diversity that we see today really did originate in the past 65 million years. It has appeared explosively. And it's because there were no dinosaurs and crocodiles in the way. And one of the things that happens when you have a lot of different taxa, a lot of different species appearing really rapidly, is you have unrelated groups starting to look the same. So for example, we have like 5 different species that are not each other's closest relatives that look like moles. We have a Eurasian mole, which is the one being held by that glove. We have a marsupial mole, that's a mole that carries its babies in a pouch. And we have an Afrotherian mole, that's a mole that's more closely related to elephants than to the European or the marsupial mole. Another example of convergence, that is the process that happens when we have lots and lots of speciation taking place very rapidly, is all of the mammals that became very large. So suddenly we have very large mammals on all of the different continents, and none of these are each other's closest relatives either. We have elephant relatives in Africa, we have rhinoceros relatives in Eurasia, and we have animals that there is no consensus on what they were related to, and they're actually all extinct now, these things called toxodon, in South America. And that's how we know, that's one of the ways we know that all of this diversity appeared so rapidly. Because on every different continent, there were these niche spaces, there were these habitats that were empty of dinosaurs that we needed to fill, and mammals filled them, and they evolved to look how you would look if you lived in that niche, rather than to look like their closest relatives. They converged into these morphologies to adapt into these niches. And very, very quickly after that extinction, Cenozoic mammals, so mammals from the time period after the dinosaurs went extinct, could do all of the things that Mesozoic mammals could do and more. Right? They could do all of the gliding and swimming and insect eating and tree climbing that mammals from the age of dinosaurs were doing. But they were also huge. They were ferocious predators for the first time. They could carry out powered flight. They were completely aquatic. They're able to do all of these amazing things that we've never seen any other animals on Earth able to do. And that's the diversity that we have now. So I'll stop here because I've been talking excitedly for an hour, but I want to leave you with a question, and that is, what's going to happen after the next extinction? We're in one now, right? We're seeing a mass extinction. We're losing, all of the animals in these pictures are endangered. This extinction feels a little bit different than just a meteorite hitting the Earth, right? It's happening in a slightly different way. Habitats are being destroyed or vacated in slightly different ways. So when we look at the amazing way that mammals bounce back from the extinction of the dinosaurs, it's interesting to think about what's going to do the bouncing back after this one. What will the third radiation of mammals look like, in other words? And who will it be descended from? Who's going to be adaptive enough to survive the human-driven extinctions that are taking place? So I'll leave you with that slightly worrisome question, I suppose. And if you have any questions for me, I can stick around and talk. I know I didn't address everything about mammals ever in this little brief class, but I have some time now if you would like to ask. And I thank you all for attending, and I hope this course has been, I know that the previous instructors were amazing, and I really hope that it's been valuable to you all.
Amazing.
Cool. All right, thank you. Like I said, I can take questions like this, or you can come and talk to me if you want to do that too.
Why was the extinction called the KPG extinction?
That's a great question. I need to, can I write something down somewhere? Maybe I can like pull up it's easier sometimes to say things in written words as well. Is there like maybe on pen and paper. So the term KPG, I'll just come to these and see that's the question. The term KPG is a combination of referring to the two time periods that the extinction separated. The Cretaceous, which was the last era of the age of dinosaurs, and the Paleogene, which was the first part of the age of man. Right? So this is Cretaceous. And this is Paleogene. Dinosaurs lived in the Cretaceous, mammals lived in the Paleogene. They also lived in the Cretaceous, as you now know. And the K for Cretaceous is because the Latin word for Cretaceous begins with a K on the C. So that's the answer to that question. But what this really means is the moment when a meteorite hit the Earth and wiped out all the dinosaurs, right? That's what that's shorthand for. Any other questions? All right. Cool, thanks. Thank you. Thank you,
Talk about when we go up next week. So we're meeting at